It's only Luke.
Are you going to this room or this room?
I'll go to my usual spot.
Luke, give me a minute.
Yep, no problem.
Yeah, I asked Dr. Berg for some clarification on the one with the, oh, you weren't in the class. I keep forgetting, you're in all my classes.
Yeah.
I asked him for.
Moses is not in the final
He
class?
I
took it
finished
last year.
one, two.
Oh, okay. So, okay.
Can I submit the quiz by paper?
Yes, that is okay.
Okay.
That's perfectly fine, yeah. I think eventually I want to promote this back. I want to quit online, right? Whenever they, hopefully in a semester or so, we'll get back.
Okay.
I generally do it that way, but I use Mathematica to do the picture.
Oh, cool.
And it makes such a good picture, I just typed it in.
Nice, nice, yeah.
Oh, I see. Okay. So Luke and Elias, Rob has some questions, so I'm just.
Yeah, what's this? What's this on the board?
What is it?
Okay.
He said, what's this on the board?
Oh, what's this on the? Oh,
It's not E&M.
oh, it's not ENM, yeah. Yeah, so think of it like this, maybe this helps. This sigma as an operator, right?
Right.
This has sum A times, first let me write this as plus. Plus minus. Minus plus. Okay. These are your labeling of the components. There are 4 pieces, right, in the matrix, if it is a 2 by 2 matrix. Now, each of this has some weight. Like these are the components. We write this vector as ij, right? I hat, j hat.
Right.
This is just a,
Shouldn't the components be inner products?
no, these are not components, these
Okay.
are ij's.
Oh, okay.
Like now, components of this ax, right?
Yeah.
Ax and ay. Let's call this here sigma plus plus, sigma plus minus, sigma minus plus, sigma minus minus. Maybe, okay, I don't know what's the standard notation. With me too long? Right. Now sigma plus plus is, you put it plus. Right. So this is a number now. This is an operator. So sigma plus minus plus would be and so on. Right, so you come up with this, maybe in index notation we do this, right? Sigma like this. Suppose A as a vector A by J. Right? Yeah, so you do E and M, right? Let me see. There's an operator that's a dyadic, right? How will I see the components? Yes, I think I can get a one-to-one correspondency between what we do in E and M and this. Okay. Give me a second. So this is A. We see this as a dyadic. Okay. I will do a 1 on the left and 1 on the right. That's perfectly fine.
Yes.
1 has this idea in, so what you would do here is that, help me here. This is in a basis, in a particular basis, this is I hat plus j hat, right?
Right.
This is equivalent to your, in quantum mechanics, summation, okay? Or without summation, this is plus minus. So this is your basis. These are your unit vectors.
Okay.
I had j hat, right? Now dotted with, right? And then your A, where here you would do the same thing. This is just sigma, let's say, or A, right? You don't write any vectors or anything. This is a 2 by 2 matrix. Here it is A, dotted with, same thing again, right? So hopefully, assuming that this is very clear by now, since you do ENM, but sometimes this itself is not clear, then it's different. Right? If that's clear, so the same thing here, plus, plus. Are you with me? Can you guys see that there, all the way there? I don't know whether it's, yeah, it's not, you guys asked, Rob asked me this, so I was answering Rob.
It's a little small, but yeah, I can still see it.
Let's see. What happened to it? It's connected, right? What do I do? I switch it off. Typically, this do that. The remote is not here. That's a new problem. Give me a time.
Batteries?
Yeah, it worked in the morning, so yeah, it could be better. Sure. So, let's just import it. That's what I always thought.
What I do with the TV remote.
Okay, well, let's see. Come on. We need this anyway because for the class anyways. This power is on. Look at this. Even okay, power switching off power. I should be able to switch off the power using this. I'm using the right remote, right? Another remote here, but that's different. Help me.
I don't know that I'm,
What kind of batteries do you take?
double A's? What like?
So small here.
Oh, no, triple A's.
Triple A's? I've got some
You carry batteries in your pocket?
calculators. Not in my pocket, just around the corner.
Oh, you're going to go to your office. Okay. Even otherwise, we need it because otherwise class cannot function actually.
I mean, can you move? You can move.
We will have to
You
move
can-
this way.
Yeah.
Okay, let's do it from the front. Maybe it sees it only from the front. I can think of. There was technical problem.
This has never happened before. Right?
Yeah.
Yeah. My guess is it probably is batteries.
Oh, something happened? Oh, I think now I stopped the camera, right? So now I have to switch it on. Okay.
So something went through. Okay, no.
Okay. Okay, now
Okay.
it's back. Okay. So put on the.
You were able to turn it off and back on.
Yeah, I think what happens is that I accidentally probably pressed on all this.
Yeah.
So this is on camera 1.
Uh-huh.
So probably I pressed camera 2, which doesn't exist.
Okay.
So all the controls fell first. When I was trying to switch off, I was
Okay.
trying to switch off camera 2, which doesn't exist again.
Okay.
So maybe you can tell Rob that you don't need the
It's
battery.
working now though? Like,
Oh yeah,
completely?
I think so. Oh no. I think so. Yeah. It is right?
Oh, so that's what it was. You had it
Yeah.
switched. Okay.
So there's assuming that like this can connect to 3 cameras.
Okay.
So I think we got it fixed, Rob.
Oh, okay.
So apparently this allows 3 cameras to be connected to this remote.
Oh,
And I accidentally pressed something where it got connected with second camera. It was trying to switch off the second camera, zoom in the second camera, move the second camera, which doesn't exist. So now I can move it, right? Yeah. Okay. Okay, so what I was saying is, yeah, hopefully, like, this is a familiar notation, right?
yes.
And this we have a feel for it, right? This times this is the first component, second component, third component, right? The same idea, plus, minus. Instead of I hat, now we are writing plus and minus. That's it. So this is equal to, if you expand this out, you will get I hat, this is your component, right? A. This is your 1, 1 component in the direction of 1. If you want, you can write it here. Plus, let me write it in the following manner, I guess. So this is equal to I hat. So I have to write the plus, but I suppose I drop it, right? Then that is I hat. There's a plus there, but if I write it as a matrix, this is this. Okay, you see that, like, this is 4 components added together. Here also it should be added together, but I'm arranging it as 4 pieces of a matrix, 4 components of a matrix. Right. That's it. So this is now, if I were to write, so this step would be plus minus. This is a completeness statement in quantum mechanics. Or the same thing like this. No quantum mechanics. This is a vector space. But then bracket notation. And this will be equal to now return as plus 1. Now maybe your hands, this has more meaning to what these are. Right? This is your component, so this was a component. This helping? Now, maybe one thing I should say is that we usually don't write this I hat, right? Because we are always in rectangular system. We choose a basis and stick to the basis. Then you can drop this. But imagine a situation where you're going from spherical to rectangular every other minute, right? Then you want to write this. And in quantum mechanics, you change your basis pretty often, right? That's what the experimenting is, right? You do your measurements in one basis, and you proceed evolve it, and then you measure it in another basis. So you're changing this basis every now and then. So you want to keep your unit vectors intact. Roughly?
Well, that makes sense. So so that explains how you justify the results.
Yes. But this is vector space language,
Right.
as well. Now the quantum mechanics part is that the interesting part is that now, like, which is different from E&M, is that first you start from here and project it in I basis. And then you project it in J basis. Classically, we have some expectations that this should be what should happen. But quantum mechanics remarkably does weird things. So that's the interesting part. But that's interpretation. But
Right.
this is the language. Oh, come on. Yeah, now it's not a problem. Oh no, what happened? Your default speaker has changed from something to something. Hello? Can someone speak?
Hello?
Luke?
Yeah, we're still here.
Yes.
Yeah. Good. Thanks. Yeah, I don't know whether that was useful to anyone. Rob asked me, maybe. Okay, at least.
That kind of explains the kind of wrapping the brain around the notation.
Yeah. Maybe I can add something because when I teach bracket notation, there is one more thing. There is now I told you that there are many bases. So in Dirac's notation, so for example, this is any vector. When you write nothing in it, this is an arbitrary vector. If you want, these are components of it. Now, he will project this in a particular basis. It could be an x basis or a momentum. So this is a wave function in the position basis. You can also say this is this is I of t. This is a Fourier transform. So that's again a very specific notation that Dirac came up with, very useful notation. But these things I think is, of course, you give the credit to Dirac, but this is a vector space line. I think that's probably what Dirac used. Again, that's a notation. Hopefully, yeah, I don't know whether maybe you guys are nice to me. It's probably.
No,
Is this what you asked?
that makes sense now because like especially when you're talking about like a projection of if you think of it as projection of I along J, then that explains why it's 0.
Yes, exactly. But again, there are two bases, remember. Think of spherical and rectangular together. Keep changing. And the basis itself is decided by the matrix. Like, I think the way to say it is, think of two vectors now, B also. A can be written in the eigenspace of A and eigenspace of B. Is the language clear of that what I said? A has a matrix representation
Right.
in its own eigenvectors. It can also be expressed in the eigenvectors of B. So that means to say that this plus and minus, whose eigenvectors are these? So there is some polymatrix that has this eigenvector. But I can say that I write A in the eigenbasis of B. That means find the eigenvectors, there are two eigenvectors there, and do this projection operators. So you can write a matrix in the eigenbasis of any other matrix. So think on that line and then ask me again. Let me not teach. Sorry, yeah. Okay, let's do some simple things. Hopefully ENM looks far easier than quantum after you the non-trivial. So who else is taking quantum? Luke, you're there in quantum?
Yes.
I'm in quantum as well.
Michael, yeah. Aliyah? Yeah, she's also. So everyone is. Jordan, you're finished, right? Yeah, Moses and Jordan, I remember.
Yes, I'm finished.
So Jordan, you tried to log in half an hour back or something, right?
Yeah, I was just free at that time. I saw you were in a meeting, so I left.
Oh, no, I was just talking this to you. seems to be set. Okay. Okay, we have. I kept the homework for due on Tuesday. You think it's not? It looks like there are 6 or 7 pages in it, but I asked you guys to do only specific pieces in there. So it can be used as a notes also, like many of it I have gone through the class, but of course class is much more detailed. And I think it is not as bad as any other homework. So don't get overwhelmed with the size of the questions there. It is easy. Okay, so let's keep it due on Tuesday so that we are go to the next part of this course. And midterm 2 is over, right? Oh, midterm 2, sorry, midterm 1 is over, so I can talk about midterm 2. But how is the midterm 1 going, then? Have you guys finished it, or you guys took the extension all the way till Sunday and postponed the whole thing?
I still have more to work on.
Lot more to.
No, I said just more to work on.
Just more to. But any questions specifically? Has anyone finished yet?
Like 2/3.
That's okay. But it's all seems like it is doable. It's just maybe mechanical. Okay, yeah. And feel free to talk to each other like to a certain extent, yeah. Or a great extent, let's say. Treat it like a homework. How about that? And I will be more critical with the grading, maybe. I think, yeah. Something like that. I think that's a bargain we can make.
That's why we're taking longer, is because we're putting every step that we can think of and explaining it.
Okay, yeah. And I think I was hard on the, I think first or second homework, right? Since you guys gave me this advice that, okay, be hard on grading. So I literally got very hard on the grading. But hopefully that was not bad. That will probably make you guys write more. And
Very good thing, yeah.
Okay. Okay, anything else?
Moses actually wrote in his homework, stop to get a drink of coffee. Well, he was putting everything down.
So you
True facts.
Oh, okay. Hopefully, yeah, I'm not being unreasonable. Okay, we were doing the magnetic vector potential for a circular wire. We finished. In principle, that is sufficient, and we can go ahead and do the magnetic vector potential, magnetic field due to a wire, because it's just L cross A. But then we can take a shorter route, not shorter, at least today the motivation will be slightly different. Okay, so this is circular. Right, no approximation, and so that's your current I. And that's here. We chose this to be your z-axis, and yeah, so yeah, J. Write everything, but J of R prime was phi prime hat I prime del of rho prime. Oh, rho prime minus A. And we got the vector potential exact expression, or is equal to phi hat for sure, mu naught over 4 pi. And then there is this
4AI.
4ai
Over the square root of z squared plus rho plus a squared.
and square root.
Yeah.
And
You have elliptic interval k, yeah. 2 minus k squared over k squared. Minus e of k, 2 over k squared.
okay. So that requires the definition of k square. So k square here, let's squeeze this in here. K square has a definition. 4a rho.
Yes. 4a rho over r squared plus a squared plus 2a rho,
Which is the
which
same
is,
as this.
yeah.
Okay. And what are these quantities in here? So that's your R, that's your rho, that's your Z, that's your A, that's your rho. Right. Okay, so once we have this, it's mechanical mostly, and you can get P of R. Like basically del cross A. That's one way to proceed with this. Or else you can start with the expression for B itself for the whole integral by Biot-Savart law, like Biot-Savart law, and get the whole thing. And again, we have an expression which shows up in your homework. Right? I don't think I asked you to derive it, but I go through the steps, and there is a similar expression for that. But we can do something simpler here, and that is that suppose I'm interested only in suppose you worry about an approximation which is very controlled in the sense you can you're interested very close to the axis. And not only that, so where exactly is this? So think of a curve like this. Pretty much 45 degrees, like think of an asymptote with 45 degrees region there. And this is a region where k square is less than 1. So if you get very close to the axis, it is very small. So this partition basically gives you the k square equal to 1 curve, and this gives you exactly where if you're very close to the axis, you're in that region. And then we can actually expand this. If k is very small, I can expand that k in power series, and I can get an approximation for magnetic field really close to this. Right? So what we can do today is that I'll get the A very close to the axis. So close to axis. So what should I write that? So k square less than 1, yeah. So we'll do the approximation where k square is very much less than 1, which means using insight, this is very close to axis. And there will be simplifications in that case. And get the A approximately for that, and then we will do the del cross A and get the magnetic field figure for that. And that is very useful often if your experiment is working in that region. So that's the idea, and that gives you a feel for how you manipulate these functions. Okay, so let's go. So this is our expression mainly, right? So let's look at what is the power series expansion for K. By the way, before I begin, is there any question on? Oh, are you guys with me? Yeah, I think. Yeah. Any question on the strategy or what I plan to do? Right. Interpretation wise, something. Okay, so K of K is pi over 2 times sometime, right? Help me if you guys have it in your. It's pi over 2, 1 plus K square over 4. Let's keep the next one. Sometimes if what you do is that first keep only the first one. How you proceed usually is that first keep only the first one. If you get something finite, you're good enough. You're looking for the leading order. If it comes out to be 0, then you go to the next one. So let's keep the first one in the beginning and then come back to the next one. So this is just for writing it 9 by 64. We don't want to keep. That's your series. And E of K is equal to 1 minus pi by 2 minus 3 over 64 K raised to 4. Okay. So first, let's go with the very the first thing you would try is that let's K of K be equal to pi by 2. E of K be equal to pi by 2. Why not? Right. And let's see what is there in this. Let me call this I, right? Let me call I to be equal to K of K times 1 minus K square over K square minus E of K times 2 over K square. That's a very naively speaking. Let's do that. And you see that, oh, that's pi by 2, that's pi by 2. And immediately there is a maybe that's not that good. What is that on? So that's pi by 2, pi by 2. So it's 1 over K square minus 1 minus 2 over K square. Right? And you notice that this is not sufficient, right? So this is pi by 2. It's not 0, but this is minus 1 over K square minus 1. Right? If I'm talking about small k, that means k equal to 0 is allowed. Right? In fact, k equal to 0 is where most of the things, very close to 0 is what happens, and this diverges at that point. Right? So I'm in trouble right away if I restrict it to this much alone. It seems like there is a divergence there, and one should be probably careful with this because there is K structure in here also, right? Yeah, so how do you see this? Yeah, let's think about this a little more, okay? So that's what it is, because that's not just saying that it is divergent is not sufficient. So let's put it back in our A expression, okay? So that's your K square. Okay.
Is that supposed to be 2 minus k squared,
Am I missing something here?
the line above? The next line up?
It is 2 minus k squared, yeah.
Oh, this one. Oh, maybe that helps. So this is 2. Oh, that is 2. Okay, good. That is better, much better. Okay, that's much better. Okay. So then that goes away, right? Yeah, that's much better. Because I was not happy with the divergence. So I was trying to interpret it right here. Okay. So it's 2 minus, so that cancels out. So that's minus pi by 2. Okay, better. This is good. Something's wrong. Okay, so we go back. Did I miss anything else, by the way? Well, okay, let's see. So what is A then? A is equal to, in that limit, extreme limit, we have phi hat mu naught over 4 pi times, so that is a minus pi by 2, and so that's a minus pi by 2. Why is it minus? This is 4ai. I divide it out by 4a rho square. And then that is 4a rho square. Square root of 2. That's correct, right? So that's k square, and there is a, yeah, maybe this is the challenge. Yeah, k square is small, right? And there's a minus pi by 2. So that's k square, that's k, right? That's k small. Yeah, how do we interpret this? My lecture in the morning also did not go well. Well, today doesn't seem to be the best day. Okay, hold on. But I'll fix it. I got it fixed in the morning. Okay, what's the interpreter? So my challenge here is that, okay, that's k square, and we are talking about k small. We know that on the axis, what is A on the axis, by the way, for a circular wire? We did that before. We said that A is equal to 0 on the axis, correct? So here, what we are not getting A equal to 0, right? So there is, this is K. If K is really small, I'm still getting with the rho, either I get a divergence, or if I set rho equal to 0 right away here, then I get a finite value, right? So it doesn't seem okay. But how do you say it? I mean, you shouldn't get contradictory things. Okay, let me interpret this. Give me a second. That's mu naught over 4 pi times 4ai, or I over rho, right? I over square root of rho. Square root of what I mean? 4 times 4. Rho is important, and this is k times minus 5 by 2. K is small, so I can take this to be small, but then there is a rho that cancels out, so you would say, oh, I'm going to go here. So rho equal to 0, so that seems to be a finite number, and that's not consistent, right? Yeah, A is equal to 0 on the axis. Isn't that correct? Did we not do that?
We did.
Yeah, we did.
Yeah, we did A. So why am I not getting A equal to, either I should get A equal to 0, or I should be able to argue that this is not consistent, or you're not allowed to go to rho equal to 0. So what's wrong in this whole thing? Again. Okay. So this whole thing is true for k small. I'm getting pi over 2. Really? Okay, maybe I have notes. Sure, I'm making some stupid mistake. Yeah, that's not good. I said this is not correct. What is going on?
What do you have in your notes?
Yeah, if I could decode that. I have 0 here.
Hmm.
If I can decode that. So let me check here. And change. So I claim, yes, so those who are online. Can we check this again? Okay, k2 minus k square. So the claim is that in this set is 0 here to the leading arc. Is this expression correct from last time?
I think I was going for that last part.
That's what I have in my notes, but someone else should confirm. Um,
That agrees with what I have in my notes.
it agrees with what you have here in your notes too.
Okay. Let me see if I can make sense out of this. Yeah, this approximation is not okay. That's the challenge. Okay,
Hmm.
this approximation, okay, I think this is a good thing to ask. Okay. So what's wrong in this? I claim this is wrong. Okay. Yeah, I claim that it's wrong. Yes, what is that's a nice thing actually. Yeah, nice thing in the sense non-trivial thing as a learning exercise. That's the idea. So this is wrong. So what is wrong? Okay. So let me do this more again. Okay. So I changed the camera. So it seems like trivial, right? So we have I is equal to K2 minus K square over K square minus K 2 over K square. And again, what did we do? Let me repeat the steps. I said this is pi over 2. I was in a hurry, not being careful. So I said, oh, this is pi by 2. This is 2 minus K square over K square minus pi by 2, 2 over K square, right? And you say that, oh, these two cancel out. And whatever is left is minus pi by 2, right? It seems all okay. Okay, it seems like what can be wrong there, right? Now let's be more careful. So I say, okay, so this is equal to pi by 2 plus order k square, right? That's what I've drawn. So order k square. That's the substitution, and this is 2 by k square, right? And let me write this as minus 1. That's okay. I want to see what am I dropping. That's all. Minus of pi by 2 plus order k square times 2 over k square. Right. So this is equal to pi by 2. So this is in the denominator. So this is pi over k square. Right. Pi over k square. Now notice that there is an order k square here. Right. So, or let me first write the easy one. So this is minus pi by 2. And next one is, so what is this? An order k square multiplied by a k square in the denominator. What is that? Order 0, right? Okay. So I'm missing an order 0 here, which is bad because this is order 0. So this is no more accurate because I missed an order 0. Do you guys see what I'm saying? This is minus order k square. The argument clear? This is something like minus pi by 2. Like minus pi by 2 is order 0. So this might be sitting inside of this. Who knows? So I have missing something here. Is the argument clear? So this is the next one will be minus pi over k square. And again, order k0. Some 2 times that, but who cares what 2 once I'm missing something. And this is pi over k square. So surely this cancels out. And this is minus pi by 2 plus some order k0. But this is meaningless because I don't know the answer. This is useless, right? Is that clear what went wrong?
Yes.
Okay. Any questions? Mike, Luke, Michael, Luke, Jordan, Alia? My mistake, I mean, it was not an intentional mistake, it was a mistake, but then this is the fix file. So how do you correct it? If you have to correct this, you have to go higher order here. I cannot skip a k square because in the denominator there is a k square. So I had to go higher orders here so that I can capture, I want this exact to this k square order. So I'll go higher order here, at least one order higher. And then I'll be able to capture this more precisely. Does that help? Okay, so let's now fix this. Okay, let's fix this now. So we do this again. So we do, this is not sufficient. So this is as well order k squared basically, right? So we don't have any answer there. Right, so we do next order, so pi by 2. And the next one is plus pi by 8, right? Plus pi by 8 k squared. This time let's be careful and I write order k4. Next one is also I drop the k4 times 2 over k squared minus 1 minus of the same thing with e. E is pi by 2 minus pi by 8 k squared plus order k raised to 4 and 2 over k squared. And then do the whole thing again. So this is equal to first term is pi by k squared over k squared. Right. Then we have minus pi by 2. Now notice this is the cancellation that was happening now, but now I have an exact expression. Right? This is pi by 8, so k squared cancels out. There's a plus pi by 4. Right? It can cancel that. Nice. So this is, and the next one is minus pi by 8 k squared. And next, and once I cancel this, this is order k raised to square now. And this one will be order k4, doesn't matter. But I'm missing an order k square. If I'm missing an order k square, then this is useless then. I should drop this also, correct? Because what's the use of writing this if I'm already missing something else? But let's keep it as it is. And next one is minus pi over k squared plus pi over 4 plus or minus plus order k squared. Okay, which is equal to pi over k squared cancels out. That happened earlier also. But now notice minus pi by 2 plus pi by 4 plus pi by 4 perfectly 0. And the next one, this is meaningless because I've already lost, plus order k squared. So even going k squared did not help because it helped in the sense at least we are consistent now. Right? Now we get this to be 0. Right? We are consistent with what we know before. But we want to go beyond this. Right? But now we know the strategy. We got to go beyond, go one more. K4, right? So we go one more. Okay. Clear? That's a very good exercise on how approximations can be dangerous, right? If we are not careful. Otherwise, you would have concluded, like, imagine this is a new problem and you really don't have any physical insight of what A is on the axis, and you would have done this in an immediate sense and you would have concluded that A is not equal to 0. That you would have got a wrong answer. But it is actually 0 to the leading order or to the order k squared. Now we go to the next. Okay. Any comments? Questions?
Yeah, I have
Yes.
a comment. I
Uh-huh.
guess it seemed to me that this second order was sufficient because like aren't we assuming that k squared is much less than 1?
Yes, k square is much less than 1. Yeah, this is good, but that whatever was the leading after that, that's 0. So you did not learn anything,
Oh, I see.
right?
So
It is 0,
okay,
which we
so k
already
squared
knew.
is the leading order. Okay.
Yes, which we already knew that it is 0, right? We want something better than what we already knew. Before there was a
Okay.
challenge because before we were getting something inconsistent. This was wrong, right? This we actually dropped this and kept this. But this was the correct thing. So we didn't learn anything from the first step. From the second step, we got something consistent, but it's not useful enough. So if you want to get something useful, we have to go to the next order,
I see.
right? Any other comments? I think it's a good, even though it was not at all intentional, I really made that mistake, but it's a good learning exercise. Okay, so we now know the drill. We just go to the next order. We again go to EI, and this time put in more terms. In fact, now that we know that everything cancels, we just have to keep the leading order. But let's do this carefully. We know that all the cancellations will still happen. It's pi by 2 k squared, no, pi by 8 k squared. And the next term is 9 pi over 128 k raised to 4. Plus order 6 times 2 over k squared. Okay. That's equal to, again, pi over k squared minus pi by 2 plus pi by 8, no, pi by 4 minus pi over 8 k squared plus 18 pi 128 k squared minus 9 pi 128 k raised to 4 plus order 4. Since it's order 4, I should drop this. I already messed this, so no point in keeping this. I drop it. I don't write it at all. That's what. And then it is minus pi over k squared plus pi over 4 and plus 3 pi or 6 pi over 128 k squared plus order 4, which is here, written in here already. Clear? Any concerns? Again, let me collect all that. So 0th order will be minus pi by 6, that should be the same. So this plus pi by 4 plus pi by 4, that again cancels out. Plus pi square and minus pi square, that still cancels out. And whatever is remaining is our leading k square, right? So the next chunk part, this is a k square. This k square comes out minus pi over 8 plus 18 pi over 128 pi, so it's this, and rest everything is gone. It's plus 6 pi over 128, I guess, right? Plus order k raised to 4. Okay. This is fine. So 8 into how much is 128? 8 into 15, I guess? 8 into 15. This is 15. So 8 plus 6, 24, 24 minus 15. 24, that's 9. Minus 9 pi.
Maybe 16.
Oh, I missed.
Yeah, it should be 16.
16. Because 48 is 8 times 6. Thank you. 6. So that will be more cancellations. Right, 24 minus 16, that's 8. And 8 goes in 120 again, that's 16, right? Nice. Right. So pi over 16, better. Thank you. Yes, that's correct. So, what you learned is that A of R is equal really it's minus.
No, it's not minus.
Oh, it is plus, right? Yeah, because that's what, yeah, it's plus, right? Okay, 24, yeah, sure. Perfect. Yeah, better, because I was thinking now how to justify the minus. Yeah. Okay. Because yesterday you asked, right, whether it should be minus or last plus, and yeah, so it is positive. Usually it is in the positive. Okay, so what is A in this limit? This is equal to mu naught over 4 pi times 4 AI over c square plus rho plus a the whole square. And this is pi by 16 k square, right? So this is k square. But k square we know now is substitute, right? So now we will stop writing this k raised to 4. We got the leading order. So we don't write that. That's equal to phi hat mu naught over 4 pi pi over 16, and this was 4a rho over d square plus rho plus a the whole square. Correct. So this whole thing is equal to like that mu naught over 4 pi. What is this? 4 cancels out. Let's say that goes as 4. This can be collected together. That's pi 4 pi a square. No, one of the 4 cancels here also, right? So that's fine. Is this correct? Good. And remember that this is your magnetic moment, right? I times pi a square is the magnetic moment, so it shows up there. That's okay. Okay, so that's a small correction. So as you, if rho is really tiny, if rho is equal to 0, again, a goes to 0, right? But if a is slightly off, you can actually get further down. In fact, often you would say that, okay, what's the point in keeping the rho here? Also, you can expand in rho, right? That's also perfectly fine. You can expand this denominator also, but let's keep that. So that's your A, and that's a relatively simpler expression than the complete expression. And now let's try to calculate B is equal to del cross A. Again, all this is true only close to axis, but now it is much more tractable expressions here. Okay. Yeah, let me see if I can do this in the next 10 minutes, I guess. Nice. Oh no, I can have more time, right? You guys allowed me to have more time. Okay. I'm really using it.
Yeah, for sure.
Yeah, thanks, John. Yeah. Okay. So B is equal to del cross A, right? So let's have so let's have del gradient crossed with. So there's a phi hat for sure. And there is a whole expression there, which is having a rho and a z in it, right? That is all there is to it. So let me write this as A, which has a function of rho and z. Notice that it has no phi dependence. All the phi dependence is in phi hat, right? Where A rho z is, that is clear, right? What I mean by that, that's the magnitude of the. So that's equal to del. So I can either act on this or on that. So this is del cross of phi hat, right, times A itself. Let's see. Plus, I can act on the other one, but then I have to change the direction. So this is minus now. Phi hat crossed with del of what gradient acts on A of rho of Z. So I don't know what is phi hat crossed with. First, let's see what is del cross phi. Del cross phi hat, but recently we have been doing this determinant, right? Let me try doing that. I typically don't use it. We have cylindrical coordinates, so this is having 1 rho 1, right? So there's only a row in that. So h1, h2, h3, right? You know what I'm doing. h1 is equal to 1, h2 is equal to rho, h3 is equal to 1, and the expression for del cross is right, h1 rho hat H2 phi hat, H3 z hat, and then d by d rho, d by d phi, d by dz, and then H1 times a rho, H2 times a phi, and H3 times az. That's your determinant formula. So it's 1 over rho of, you have rho hat, rho times phi hat times z hat. This is d by d rho, d by d phi, d by dz, and a rho. So this is just phi hat at this stage, right? So this is 0, 1. Oh, what's that thing? No, H2, there is a rho. Like rho times 1, the phi hat has only 1 and then az. That's clear? Put it in. Okay, so this is equal to, when it is rho hat, it contributes. When it's rho hat, no, rho hat, it doesn't contribute because d phi is 0, dz is 0. Rho phi hat, this contributes. So this is phi hat. Just phi, really? Yeah, just phi hat, it contributes. And z hat, no, z hat, it contributes. So phi hat,
That's 0.
phi hat is 0, right? And z hat, it contributes. That's it. This is z hat. There's a mistake. Dimensionally wrong, right? Because z hat has a 1 over. Okay, so what about phi hat cross gradient? That is probably easier. Phi hat crossed with rho hat, d by d rho plus phi hat rho d by d phi plus z hat dz. Phi hat crossed with rho hat plus minus z hat. Phi hat crossed, phi hat that's 0, phi hat crossed with z hat is rho hat plus rho hat. Great. So P is equal to E is equal to rho hat z hat times a, so that's z hat times rho times a of rho z minus plus minus z hat d by d rho plus rho hat d by z of a. That's equal to z hat over rho times a, the magnitude wise, this is mu naught over 4 pi times I pi a square over rho divided by z square plus rho plus a the whole square, 3 by 2 plus d by d rho plus 4 hat d by z, and again this is mu naught over 4 pi okay. The rho here cancels out. So that's equal to, so that's your leading expression, right? We know that leading expression, the magnetic field does exist on the z-axis. Right? So that's your leading term. So it's
In that first line for B, that should be a minus sign.
this one,
That, yeah, both of that should be minus.
good. So this is minus.
Yep.
Thank you.
Yep.
Otherwise I'm in trouble. So this is, let's say, plus, and this is minus. Okay.
Yeah,
more?
yeah. No, you're good. You're good.
Yeah, catch me. So this is what you would have got if I had not kept the correction. A square over z square plus rho plus a the whole square. But now the rest of them are with the corrections, the derivative terms that come with this. So there is a correction on the z hat direction, plus z hat direction mu naught over 4 pi I times pi square. Let me keep. There's two places where rho can hit. This probably is the higher order, but still, let me do that. So this is equal to d by d rho. So that's 1 over z square plus rho plus a square and 3 by 2. And correct, right? I think so. And there's one more term when I hit the denominator, and that is minus 3 by 2 of z square three by 2 derivative, right? Minus 3 by 2 minus 1 by 2, so that's 5 by 2. And 2 times the rho plus a, and then take the derivative with rho, that's done. And there's already a rho there. Okay.
Hard job, find the mistake.
No. I think this can get complicated very quickly. So at this stage, if I leave you guys with a mistake, I think zero loss. It's just that I'm seeing a row in front. Like why I'm bothered about is that I know that magnetic field is supposed to be only this when rho is equal to 0. It seems like when rho is equal to 0, this goes away. This again contributes, which I'm not happy about. So I'm seeing that there is a row in my notes. So I'm wondering where did it show from. this okay? Is this okay? Yeah, so this becomes 2, right? Yeah, actually this is necessary because this is not the answer. In the actually, if you calculate b on the axis, there is the factor of 2, so this is important. So it is all okay. So at rho equal to 0, you would think that this is 0 and oh, there is an extra term, but this was actually necessary to get this down here. So in the leading order, you wouldn't get that. Right? So it's remarkable then that this actually is 1 plus 1, 2. So there is a factor of 2 there. So if you had dropped that term, this k square term, you would get the wrong answer for B. Right? So again, a typical thing that you want to keep all the leading orders, whatever contribute. Yeah, so this is okay as far as I can see. Yeah, we'll get the final answer in a moment. So dy dz similarly, so there's only one place I have to get, right? So that's easier. So plus a minus rho hat. Give me a second. Here, minus rho hat. Or maybe can I use my extended board? Yeah, let me use that, then I don't have to write down again. So this is similarly minus rho hat times mu naught over 4 pi I pi a square rho, and we do the same idea, z square plus rho plus a the whole square 5 by 2, and again there was a minus 3 by 2 which made this plus 3 by 2, and it is 2 times z, just taking the differentiation. So overall we have a z component original correction. So this is b, z hat mu naught over 4 pi times I times pi square times a factor of 2. Put these two together, and the next term is slightly off. This is on the axis. The next term is off the axis, so this is minus. You know, it slightly gets weaker if you want to think of it like that. Z component gets slightly weaker. I, so 3 is I pi a square, and 3 times rho times rho plus a. This is the head component, and so notice, remember how we are talking about, so this is the z-axis, correct? That's your ring, and the magnetic field we know will be along here, and that's slightly off, right? That's your magnetic field for a ring. So we are talking about slightly, so this was in the z direction, now there is a z component and a rho component. So this is the extra rho piece that shows up here, what's the magnitude of that. So this is plus rho hat and mu naught over 4 pi times I times pi a square times 3 rho z over okay. I think so. Yeah, 3 rho z.
Isn't that middle term of 5 halves?
5 halves. What was 5 halves? Oh, this is 5 halves. Yeah, this is. Yes. Yeah, everything else is okay. Right? Again, see the interpretation down here. So Z component has slightly reduced and rho component has slightly increased. That's the amount of increase and steps. Okay, that's all. Thanks for allowing me this extra time. Yeah, it's helping. I try not to use it all too often. Yeah.
Should have stayed Tuesday, nobody showed up for the tutoring.
So, but there are regular students this time. Last time I remember you had a regular student
I'm having
off and on.
my regular, the one that I had last time, who was regular, she's mad at me because I'm not constantly available. Because when I'm using 405 and it's a chalkboard, I told her that a Zoom meeting would be useless because it's not going to show up. It just doesn't have the contrast that this board does. And that she was just getting frustrated, but I have, I gave her my schedule for my other actual Zoom meetings. I haven't heard from her.
Okay. Yeah.
And the other Monday night was odd. I had a student that came in, and he was acting as he was completely confused. And so he asked me a question, it was a clarification question, and I explained what it meant. He's like, "Oh, well, that's all I have. 5 minutes."
So you clarified it in line, so that's good.
I really think
Someone came very confused and in
misspelled something.
one sentence, everything got clear.
It was not a major question that I answered. It was, I thought, oh, this young man's going to have several questions. But I answered back something that I wouldn't have thought would have been a problem for somebody. He was done.
Hey, Dr. Sujesh,
Yes.
can you explain that diagram that you drew?
Oh,
The
yes.
circle, I think I missed it.
Good. Okay. Now what is happening here is that okay, if you interpret your B here, right, in the answer, there is a, can you see what I'm writing now?
Yes.
The board? Yeah, okay. So B has, let's call that B0, right, in the Z hat direction, plus there is a B1 in the Z hat direction, plus there is a B2, let's not call it B2, let's me call this B1Z, and this is B1 row in the row hat direction. Good with me?
Okay.
Okay. If I had not done this correction, these two terms wouldn't have been there, that's just this. So I have this ring, we know that the magnetic field looks like a magnetic, so for a ring, the magnetic field looks like this. The exact ones. Okay, is that clear?
Yes.
Right. So now, if I were to not keep this, I would have got on the axis just the magnetic field, this one. Just this piece. Vertical.
Okay.
But now I'm making a correction. What has happened is that this is actually negative. So this has shortened a little, and I have a small component in the row direction, which means I have a small bend. If I go slightly away from the axis, right? And that's that. So this is that curvature that you're getting this one.
Okay. Okay, I see.
Where the magnetic field bends a little as you go away from the axis, that's the bend you're catching.
Okay. That makes sense. Thank you.
It should be useful if your experiment is really close to the axis, then this might be sufficient instead of keeping the whole elliptic. But these days, most of the times, numerical programs are really efficient. It's easy to work with. So you would as well keep the whole elliptic function, even if you're close to the axis. But there will be situations where you might want to do this, especially 50 years back, you would really need this.
Okay. Thank you.
Yeah, you're welcome. Yeah.
I have one question.
Yes, you.
I'm not exactly sure how to phrase it, but I'm just gonna like start talking. So the I times pi a squared term, like that is the magnetic moment.
Mhm.
Yeah, but that is like inherently the magnetic moment should be a vector, right? So this is the magnitude of the moment.
So it is
So
M. If you put it with Z, it is M. Because
right,
directly has the Z happening, right? Yeah.
right. So then the interpretation is is the interpretation that along the axis the magnetic field is exactly or is proportional to the magnetic moment, but slightly off the axis, it's only proportional to the magnitude, right? Because it, like, the magnetic moment doesn't have a rho hat component,
Yes. So
right?
yes, you're correct. Typically, it is rho. I think the best way to see it is, yeah, I see here, Christian. I think.
Yeah, is it a meaningful question or am I just
I think you're
okay?
trying to ask that on the z-axis, is it always purely m hat? It's in the direction of m, right? That's your
Mhm.
proposal. And I think that is correct because if you had a point dipole, we know that A is equal to m crossed with r over r cubed, right? If it was really small loop,
Mm,
that is exact.
right.
And magnetic field, there's a mu naught over 4 pi, of course. And magnetic field is 1 over r raised to cube times in the direction of m. I think it is 3 times m dotted with r hat minus m, correct? Minus of plus, probably the minus. And
I think
now,
there's another,
and
r hat, like
oh, it should be a
3,
vector, of course. Yeah, it should be a vector. Right?
yeah.
Right. Now say that you're on the axis, correct? On the axis, this is z hat. R hat is z hat.
Mhm.
So you get 3 times m, right? Because m is in the direction of things. So there's 3 times m minus of m, z hat, which is you get 2 times m over r cube times z hat, which is exactly what you're saying. So it is 2 times m over r cube, correct? So it will be in the direction of, so I think that's a correct conclusion that on the axis, it is always proportional to m. And this also gives you an idea of what it will be off the axis. Off the axis, it should be of the form r crossed with m crossed with r. So that's the structure that is coming up, but this is more the broken
I
up.
see.
Yeah. So I think that's a correct conclusion. Does that help? Was that the question?
Yes. Yeah, that was the question. I'm starting to think that my question was sort of trivial because if the magnetic moment is on the z-axis, then of course, if the magnetic field is on the z-axis, they're parallel. So I'm not sure if my question was meaningful, but yes, I think.
But yeah, its conclusion is correct. I think.
Okay, yeah.
Maybe after you
I
analyze
see.
it, you're sort of trivial, maybe. But but at the beginning maybe you wouldn't accept it. Yeah. So it's okay.
Right. Yeah, yeah, thank you.
Well, that's interesting. I mean, how you express it off the axis. I mean, that is curious to me as well.
Okay.
Because you wouldn't write vector M in the row hat component. But you're saying it could be expressed as R cross M cross R.
Exactly. Yeah. So this is not really ham, but it's component, yes, project.
Mm. Okay, I see.
Okay. I think it's pretty long. Talia left. Her kids were bothering her. Yeah.
Yeah. All right, thank you so much.
Yep, thank you.
Yeah, thank
Bye.
you. Yeah, guys. Yeah, good questions. Yeah.
See you guys later.
Yeah.
But Michael is